And what we want to do is understand the concept of a tangent line approximation, compare the value of the differential dy with the actual change in y, or delta y, estimate a propagated error using a differential, and find the differential of a function using differentiation formulas. So first, let's talk about tangent line approximations. So in this section, you will look at examples in which the graph of a function can be approximated by a straight line. So to begin, consider a function f that is differentiable at c. The equation for the tangent line at point c, comma f of c is given by y minus f of c equals f prime of c times x minus c. That is just the point slope form of an equation. Y minus y1 equals the slope times x minus x1. Remember, c is your x1, f of c is the y value at c, so that's your y1. M is just your slope, which is the derivative at the point of tangency. Okay, if I just solve that for y, if I solve the equation line for y, I just add f of c to the other side and I get this. And that's called the tangent line approximation or linear approximation of f at c. Okay, so nothing new there. The notation might look a little bit different, but it's nothing new from what we've done before with tangent lines. So because c is a constant, y is a linear function of x. Moreover, by restricting the values of x to those sufficiently close to c, the values of y can be used as approximations to any desired degree of accuracy of the values of the function f. In other words, as x approaches c, the limit of y is f of c. Let me just show you with a little picture, and I'm sure we'll get a picture in a minute here. If that's your point of tangency right there, your tangent line touches the curve right at that point. Pretend that touches the curve right there. At x values near the point of tangency, the tangent line and the actual curve are very close in value. The y values are very, very close. In fact, the closer you get your x value to be at the point of tangency, the closer the y values will be on the graph and on the tangent line. That's why the limit as x approaches c of y is f of c. So the limit of the y value on the tangent line as x approaches c, as x approaches the x value, the point of tangency, the limit is the same as the function value at c, because that's the point where the tangent line and the actual graph touch. Okay? Now, why this is important is because it's much easier to evaluate a line like y equals mx plus b. It's much easier to evaluate that because all you're doing is multiplying and adding. Okay? It's much easier to evaluate that than some complicated function. So if I know my tangent line approximates the value of a function, then I can use the tangent line to get approximate values of that function for values near the tangent line. Okay? So find the tangent approximation of 1 plus x minus x cubed over 3 at the point 0, 1. Then use a table to compare the y values of the linear function of those of x, f of x on an open interval containing 0. So the first derivative is 1 minus x squared. So the equation of the tangent line is y minus f of 0, or y minus y1, equals the slope times x minus 0. All right, f of 0, if I plug 0 into the original function, you get 1, and that's the point right here, 1, and 0 goes in for the c. And f prime is 0, the derivative evaluated at 0 is 1. So if I solve that for y, you just get y equals 1 plus x, or x plus 1. So for values of x near the point of tangency, so near 0, the tangent line, and they have the wrong function in there. It is 1 plus x minus x cubed over 3. So it'll be 1 plus x minus x cubed over 3. Okay. So values near 0, the y values are very close to the y values of the actual graph. Okay? So they're very close. But the further you get away, the less accurate the tangent line approximations are. Again, this is 1 plus x minus x cubed over 3. Okay? See, the tangent line actually cuts through the graph right at that point. And as you get closer to the point, the tangent line and the graph kind of line up, and the further away you get, there is a larger difference. Okay. So notice that the closer x is to 0, the better the approximation is. All right, and that's what we wanted to illustrate with tangent line approximations there. All right, stay tuned for the next video.